Okay, question. What is this? November 2016, paper 2 times N2, and we're given two functions. I like this question because these two functions, you don't learn them in IB, but they are hyperbolic sine and hyperbolic cosine. You might have to check this out, look this up, but I'm pretty sure the first one is hyperbolic cosine and the second one is hyperbolic sine. And they're closely related to the trigonometric functions. And this first one is also the solution to the shape of a weighted chain. Okay, so part A, part 1, straightforward. We're doing 1 over 4 lots of f. 4 lots of f. In the red there is 2e to the x plus 2e to the minus x, and then minus 2 lots of the blue is minus 1e to the x plus e to the negative x. With a bit of simplifying, that becomes 1 over e to the x plus 3e to the minus x, and then just times it top and bottom, e to the x, e to the x, to give you e to the x over e to the 2x plus 3. Okay. B part 2, we're going to do a substitution to integrate. We're not integrating 1 over 4x minus 2g of x, we're integrating the function we've just found, e to the x over e to the 2x plus 3. Using the substitution, u equals e to the x. If u equals e to the x, we can differentiate that. Just realised I missed the dx there. Differentiate u to give you du by dx is e to the x, or dx is equal to du over e to the u. And now we can put that into our integral, and we're going to get e to the x over e to the 2x plus 3 times, well, instead of dx we're going to have du over, oh dear, sloppy, over e to the x. That cancels top and bottom, e to the x. So all that remains is to use our substitution to substitute into there, and we get the integral of, well, it's just 1 on the top, or du on the top, if you prefer. E to the 2x becomes u squared plus 3. And that is one of our standard integrals. It's in the formula booklet. 1 over root 3 arctan u over root 3. Now, I'm going to put a little pin in that because we've done all these integrals and we haven't thought about limits, so let's go back to the start and have a look at the limits. So we started out with the limits in terms of x as 0 and log 3. And we were told to use the substitution u equals e to the x. When you do that substitution, the limits that we're using also change. So those red highlighted ones are x values, because we were differentiating with respect to x, and we need to change them into u's, so I can put them there and there. That's easy to do. We just evaluate u when x is 0, which is 1, and we evaluate u when x is log 3, which is 3. So that's the integral that I'm doing from 1 to 3, and we can substitute that in to my expression. 1 over root 3 arctan 3 over root 3 minus 1 over root 3 arctan 1 over root 3. Now, we're not out of the woods yet, because I need to turn that into the form that has been specified, which I will remind you is here. Pi root a over b. So let's think, can we evaluate either of those two things? Well, one of them is relatively trivial, this one, because you should know arctan of 1 over root 3. So what about the other one? Well, this might not look obvious, but if you do a number divided by its square root, you just get that square root. 3 divided by root 3 is root 3 by definition. So this is the same as 1 over root 3 times arctan root 3 minus arctan 1 over root 3. And now both of those things we know. Arctan root 3 is pi by 3. Arctan 1 over root 3 is pi by 6. So that becomes 1 over root 3 times pi by 3 minus pi by 6, which is 1 over root 3 times, what is that, 2 minus 1 pi over 6. And we just have to rationalise that, times it by root 3 top and bottom, to give you pi root 3 on the top and 3 times 6 on the bottom. And we're done for part A, which was the big 9-mark part. Okay, part B. Got a quadratic equation but we're going to solve this. Well, we've got this new function, so let's write out what that function is. H of x is equal to n lots of f of x. So that's n e to the x plus n e to the minus x over 2 plus 1 lot of g to the x, e to the x minus e to the minus x over 2. With a little bit of rearranging, that becomes n plus 1 e to the x plus n minus 1 e to the x all over 2. And we want to solve when that equation is equal to k. Okay, so that's all we're doing, solving when that's equal to k. So, oh, lost the minus there, look. So, let's multiply everything by 2. N plus 1 e to the x plus n minus 1 e to the minus x equals 2k. Set it equal to 0. N plus 1 e to the x minus 2k plus n minus 1 e to the minus x equals 0. And it gave us a clue that we're looking for a quadratic equation. You should be getting used to this. I've put these in ascending powers or descending powers of e to the x, right? There's 1 e to the x, then none, then negative 1. So it is a quadratic equation already, but we'll make life a little bit easier if I multiply everything by e to the x. To give me n plus 1 e to the 2x minus 2k e to the x plus n minus 1 equals 0. And now I can solve that using the quadratic formula. E to the x is equal to minus b, so 2k, plus or minus the square root of b squared, so that's 4k squared, minus 4 times n plus 1, n minus 1, all over 2 lots of n plus 1. Now if I'm solving an equation, I need to get x, not e to the x, so I'm not done. But I'm going to tidy this up first because everything's divisible by 2. 2k is divisible by 2. Root 4 is divisible by 2. And 2 is divisible by 2. So this becomes k plus or minus the square root of k squared. And whilst I'm about it, let's expand that bracket because that is the difference of 2 squares. So let's write minus n squared minus 1 all over n plus 1. And I want to get x on its own, so take natural logs of both sides, and I get my final answer, which is x is the natural log of k plus or minus square root of k squared minus n squared minus 1 all over n plus 1. Right, in order to get 2 real solutions, what do we need to show? Well, we can only take logs if this number is bigger than 0. So it has to be true that this fraction, this numerator, is positive. And to get 2 solutions, they both need to be positive, and the smaller one is obviously that. Has to be greater than 0. And also, in order to get 2 solutions, I have to be able to take the square root, which means the thing inside the square root, the discriminant, also has to be positive. K squared minus n squared plus 1 has to be greater than 0. So let's look at the blue one first. We have k squared has to be greater than n squared minus 1. Oh, that's what we were asked to show. What about this bit? This gives us k has to be bigger than the square root of k squared minus n squared plus 1, which, if we square both sides, which is only true, well, we can square both sides, but times both sides by k, this step is only true if k is a positive number. If k is negative, then what would happen is for negative k, the inequality symbol would switch. So let's look at those two scenarios, the red one and the purple one. In the red one, we end up with 0 is greater than 1 minus n squared. Which is true because n is bigger than 1. It's given here, look. So that's always true. But this one, this gives us 0 is less than 1 minus n squared, and this is never true. So k can't be less than 0. And it's easy to miss that that's a requirement of this question, look. It asks you to show that k is in the positive reals. And in order to do that, you need to go through these steps here to conclude that k has to be bigger than 0 and k squared has to be greater than n squared minus 1. Okay, we've now got a new function, t of x. It's g of x over f of x, hyperbolic sine over hyperbolic cosine. It should be no surprise to learn that t, and this is why they've picked the letter, represents hyperbolic tan. Again, don't need to know that. Just a little bit of background information. So we've got t of x is equal to e to the x minus e to the minus x over e to the x plus e to the minus x. But it's probably easier just to think of it in terms of g and f, because we have this property. If you differentiate f, you get e to the x plus e to the minus x over 2, which is g. And if you differentiate g, you get f. So, if I want to differentiate t as g of f of x, t dashed of x becomes v du by dx, that's f of x, g dashed of x, minus g of x, f dashed of x, all over f squared of x. And we're very nearly there, because I know that g dashed of x is the same as f of x, and f dashed of x is the same as g of x. So I can rewrite this as f of x squared minus g of x squared all over f of x squared. Last part of this mammoth question is to show that t dashed of x is greater than 0 for all x. Well, if t dashed of x is greater than 0, that must mean f of x squared minus g of x squared has to be greater than 0, or that f of x has to be greater than g of x squared. In fact, and the reason that that is true is because the denominator, f of x squared, is obviously positive. So but this is true since e to the x plus e to the minus x over 2 squared is bigger than e to the x minus e to the minus x over 2 squared. If you want to convince yourself, you can always multiply that out and see that they are the same, except for on the left hand side you get e to the minus x, and on the right hand side you get minus e to the minus x, or 2. There are 2's there as well. If you like, over 2 ends up cancelling down. It's a bit hand wavy. The finer details I'll leave you to go through yourself. But it should be obvious that the left hand side is bigger than the right hand side. And you're done.